von Karman momentum integral equation. We obtain tau w in terms of the momentum thickness, and that is the expression that we have with eta is equal to y by delta. The momentum thickness is written like this. And so, for self-similar solution, this integral is invariant with this x. Let this integral be represented by alpha. Now, alpha is not a function of x. For self-similar solutions, the kind that we can assume on a flat plate for sure. For many other geometries, we get self-similar solutions, but that is beyond the level of this course. The shear stress at the wall, the left-hand side of the equation, can be written as tau w is equal to mu du by dy at the wall, and which can be shown as equal to mu u by delta times f double prime 0. Therefore, rho u square alpha d delta by dx is mu u by delta times beta, where beta is f double prime 0, that is d of non-dimensional u by capital U with respect to y by delta. And we name this beta. So with this beta, I get an equation alpha delta d delta by dx is equal to nu by u beta. Now, alpha and beta are known once we know the shape of the velocity profile, and that's independent of x. So this equation can be easily integrated to give delta is equal to under root twice nu by u beta by alpha x for the condition delta is equal to 0 for x is equal to 0. The boundary layer thickness at the start of the plate is obviously 0. This is the essence of the Karman momentum integral method. Von Karman, one of the greatest name of fluid dynamics, of almost the same stature at Prandtl, proposed that the value of beta and alpha are quite insensitive to the actual shape of the velocity profile, as long as we meet the basic requirements of the velocity profiles. And what are the basic requirements of velocity profile? U at the wall must be 0. V at the wall must be 0. And at the edge of the boundary layer, U must tend to capital U asymptotically. That is, the derivative of the velocity profile should also tend to 0 as y tends to infinity, or at the edge of the boundary layer. So, von Karman proposed that choose a velocity profile to meet these conditions. And if we do this, evaluate alpha and beta, which are simple integration, and then the growth of delta can be obtained in this manner. So the method has the following step. Assume a profile which meets the required condition at the wall and at the edge of the boundary layer. calculate alpha and beta for the profile, plug them in the integral equation to get the variations of delta with x. In this table, we have tried three different profiles: linear, parabolic, and cubic, and compared them with the exact profile. Really not exact, but the solution obtained by Blasius. For the linear profile, we need only two conditions. F0 is equal to 0. The velocity at the wall is 0, and the velocity at the edge of boundary layer, u by capital U, is 1. A linear velocity profile. For this, the value of alpha is readily obtained as 1 over 6. The value of beta, which depends on the slope of the velocity profile, is obtained at 1. Delta by x is then obtained as 3.46 divided by under root Reynolds number, and the skin friction coefficient CF is evaluated as 0.73 divided by under root REX. For a parabolic profile, we need three conditions, and we use them. F0 is equal to 0, F1 is equal to 1, and F prime 1 is equal to 0. The slope of the velocity profile at the edge is also 0. F is equal to twice eta minus eta square meets these three conditions, and for this profile, the value of alpha is 2 by 15, the value of beta is 2, and we can calculate delta x and CF. For the cubic profile, we need four conditions. So it is not just the velocity tends to 1, but the first derivative of the velocity and second derivative of the velocity are also 0 at the edge of the boundary layer. So with this four condition, the cubic profile has this simple form. For this, the values alpha is obtained as 39 by 280, beta is 3 by 2, and these are the value of delta x and CF. For the Blasius condition, we get the result delta by x as 4.91 and CF as 0.66 divided by under root REX. The Blasius solution in his day took months of calculation on mechanical calculator. And for Karman, results were obtained in minutes. And you can see that the results are quite accurate. That is the power of integral methods. Obtain very quick results which are good enough for most purposes. The comparison of the three profiles that we have chosen, the linear, parabolic, and cubic profile across the boundary layer compared to the actual profile due to Blasius, which is shown in black. Now, all this development is for the laminar flow, because the nature of the velocity profile that we've taken. The Blasius profile is only for the laminar flow, because we have written shear stress to be mu times del u by del y. In turbulent flow, that will no longer be true, though at the wall the shear stress is still mu times del u by del y, but that is within the laminar sublayer at the wall. As the distance along the plate increases, the value of x increases, the Reynolds number Re based on x increases, and at a value of about 5 into 10 to the power 5, the boundary layer becomes unstable and becomes turbulent. And the growth pattern of the boundary layer changes. There isn't sufficient theory for the turbulent boundary layer. Various attempts have been made, and the structure of the turbulent boundary layer is too complicated to be discussed at this first course level. But today, using direct numerical simulation of the Navier-Stokes equation, researchers can calculate the turbulent flow on flat plate or any other shaped body with great amount of accuracy. Here we will discuss some very elementary ideas of what we can do with the turbulent boundary layer. First of all, notice that the velocity profile across the boundary layer in turbulent flow is very different from the laminar flow. The Blasser profile is shown in blue, and the turbulent profile is shown in red. The slope delta u by delta y at wall, that is at y is equal to 0, is very sharp. And then the growth is slow. In fact, notice that we have been able to obtain the momentum integral equation without any regard to whether the flow is laminar or turbulent. However, we have used the viscosity relation to evaluate tau w. Even in turbulent flow, the velocity at the wall vanishes and the shear stress at the wall is evaluated from the same law. This suggests that we can use the Karman integral method for turbulent layer if we can use an appropriate velocity profile to evaluate the momentum thickness and the integrals alpha and beta used in the integral equations. Prandtl pointed out that the turbulent profile can be approximated by a 1/7 power law observed in flow through pipes. That is, u by inviscid velocity capital U is y by delta raised to power 1/7. The red line here is what I have plotted, 1/7 power law. This is very close to the turbulent profile. This was first experimentally obtained in flow through pipes. And the Prandtl also suggests that we could use the expression for the shear stress at the wall from the pipe flow itself. And for the pipe flow, he had obtained tau w divided by rho u square as 0.224 into Reynolds number raised to power 1 by 4 for turbulent flow through pipes. With these, the value of delta 1 and delta 2 are obtained as delta by 8 and 7 delta by 72. And then from the momentum integral equation, using the appropriate relation for tau w, we obtain that for the turbulent flow, the thickness of the boundary layer grows like this. This table shows the difference between the laminar and the turbulent flows. You see the boundary layer thickness in the laminar flows grows like x raised to power 0.5, like under root x, because there is x in the numerator and there's a root x in the denominator. Reynolds number based on x contains x in the numerator. So when we take square root of that, we have x raised to the power half. And so the net variation of the boundary layer thickness in the laminar flow is like x raised to the power half. And for the turbulent flow, by the same argument, this is like x raised to the power 0.8. The displacement thickness in laminar flow is 1/3, about 1/3, a little more than 1/3 of the boundary layer thickness, but in the turbulent flow, it is only 1/8. The deficit of mass flow is much less. Similarly, the momentum thickness from 0.134, it reduces to 0.097. The shape factor values reduces from 2.59 to 1.29. Turbulent flows are less likely to separate. Skin friction coefficient decreases as root x in laminar flow, but x raised to the power 1/4 in the turbulent flow. This graph shows typically the variation of drag coefficient with Reynolds number. The transition occurs at a value of Reynolds number based on the location distance x of about 5 into 10 to the power 5. The drag coefficient reduces at a much lower rate in the turbulent flow than in the laminar boundary layer. Thank you very much.